thanks to the Mystery folks for asking me to give a presentation on something that I get a lot of questions about. I do quite a number of research talks on the applications of quantitative NOE, NOE distance analysis, but getting into the nitty-gritty of the practicalities is something I've been meaning to do for a long, long time. So hopefully this can give me an opportunity at some of the things I brush over when I present this work more generally. So the work in my research group, just to kind of put this into context, works around three things really. Almost a virtuous circle of NMR method development, where we're trying to develop new ways of measuring information, whether that be information that we can already get, like NOEs and so on, or whether that be new parameters, new bits of information that aren't really being used in the NMR community. And the second part of that is taking that data that we can experimentally measure and analysing that in a way that gives us quantitative information which we can then use to work out detail about molecular structure, molecular dynamics, in particular in small molecule science. And then once we've got that data and we've extracted and analysed it, we compare that to some model system that we may be interested in, generally using a lot of computation to develop models for the molecular systems that we're trying to study and trying to fit the parameters that we measure experimentally to those, so we can confirm those models or indeed find out that they're complete and utter rubbish. So the talk today, quantitative qNOE, or quantitative NOE distance analysis. I'd like to talk about a few things: why we would want to do it, how it can help us in studying molecular structure, molecular dynamics, the practicalities of doing those experiments, why and how we do them the way we do, and then particularly how we analyse the data that we get out. And the real devil is in the detail of how you analyse this qNOE data to extract information which is quantitative and accurate for a certain value of accurate. And then looking at when things get tough, so moving from systems where the NOE and the distance don't directly mean something, systems with molecular flexibility. If a molecule's got 55 conformers, then measuring a distance of 2.2 angstroms might not necessarily tell us something directly about that molecule, and we have to use computation and qNOE to tease out the meaning of that data. And then I'll demonstrate all of this, applying this to a couple of case studies that we've worked on over the past 2 or 3 years, and just try to show you the power of this technique, but also some of the pitfalls you can run into. So here's one of the first cases that we looked at that really got us into this field. This is conocosterol F. It's a molecule that basically a steroid type backbone, was isolated from Theonella swinoi marine natural product, it's a sponge. And the 2D structure, or the connectivity of this molecule, was relatively straightforward for our collaborators in Italy to work out, but they really struggled to work out the stereochemistry of the epoxide in the center here. And the reason for that is that epoxide is a doubly quaternary epoxide. There's no protons on the epoxide. In fact, 2 of the centers off the epoxide are also quaternary, so really you have to use a lot of indirect information to find out about the stereochemistry of this epoxide. And if we look at the 2 possible stereoisomers, the epoxide up and the epoxide down, we can see that actually the growth structure doesn't change very much. So using something like NOEs that tell us about whether 2 protons are close in space to each other isn't actually going to help to differentiate these structures, because in both cases those protons are close in space. It's not a question of are they close in space, it's a question of how close are they in space. And that's where we really got into this game, because if you model these 2 structures, you can see that there are subtle differences in the interproton distances in for example, the proton-proton interactions that I've shown here. And so if we can measure the distance between these protons accurately enough, we should be able to differentiate between 2.45 and 2.7 angstroms, certainly between 3.2 and 4.4 angstroms. So all of the work that I'm going to be talking about today arises from the nuclear overhauser enhancement, the NOE. Now I'm not going to go into the background of this in enormous detail. I'm going to assume that you have an idea about what NOEs are and where they all come from. But roughly speaking, they're a nuclear relaxation phenomenon arising from dipole-dipole coupling, which essentially is you perturb one nucleus, one of these pictures of the Earth, and that will induce a perturbation in a second nucleus if those two spins are close in space to each other. So dipole-dipole coupling, so it scales with the distance between those two nuclei. Now experimentally, there are two basic types of NOE experiments that we might use or have been used for NOE analysis over the years. And the first of those is saturation NOE, what might traditionally have been an NOE difference spectrum. So a saturation NOE essentially builds on an experiment where you selectively saturate, if you're going to do a selective saturation experiment, one nucleus, S. You therefore equilibrate its populations in the alpha and beta states, and that will then perturb the population of another spin I that is near to S in space, if they are near to each other in space. And the way that you conduct this in a practical sense is you run two experiments. You run one where you're selectively saturating S and one where you are not. And you subtract one experiment from the other, and the difference between them arises from this perturbation in the population of any spins which are near to S in space. And the trouble we've got with NOEs is they are really, really weak. You're talking about peaks which are on the order of 1%, 0.1%, 0.01% of the intensity of the original proton spectrum. So any variation between the selectively saturated NOE spectrum and the unsaturated experiment, or the off-resonance saturated experiment, any variation between those two which is not due to NOE is going to show up as an artifact in our spectrum. So traditionally these kind of NOE spectra were very weak, artifact-filled, and because it's an equilibrium NOE that we'd be looking at with a saturation NOE experiment, it's not very helpful for measuring distances. You can do it, but it's not something we're going to deal with today. Instead, we're going to look at the transient NOE experiment, which is, relatively simply put, an inversion of the population of one spin, and then that encourages inversion or causes a perturbation in the population of a second spin I, which is close to it in space. So experimentally, we do this in a couple of ways. In a 1D NOE, it's very easy. You just selectively invert S, wait for a period of mixing time, and then measure your spectrum and see what's happened to spin I. In a 2D spectrum, you just do the same thing, but with a T1 evolution period in order to extract the second frequency. So the end result of these two experiments is grossly the same. I'm going to talk a lot about 1D NOESY data today, but you can do exactly the same experiments with 2D NOESY, with a couple of exceptions, and just using slices out of the 2D NOESY, horizontal slices, in order to extract what look like 1D NOE spectra. And you can do the same sort of analysis as I'm going to show you today. So we're worrying about transient NOEs in the main. So here's the first bit of the practical side of things. In terms of sample preparation, I get asked a lot, what do you do? How do you degas your sample? What's your relaxation delay? How do you make sure you're in the initial build-up, initial rate region of the NOE build-up curve? And the bottom line here is we don't actually do a lot very special. We dissolve our sample up in a standard sort of solvent. A general rule of thumb is you want the sample to be relatively low viscosity if you can, so that your samples, your molecules are tumbling relatively freely in solution. So for biggish molecules, where I'm talking greater than 200 molecular mass, then a low viscosity solvent is useful. If you've got really small molecules, actually you find that NOEs of this type don't work very well when you're talking about molecules with a mass of 150 molecular mass or less. You get killed by relaxation. You can still do it, it's just not quite as easy. But if you're working with a bigger molecule and you're putting it into DMSO, you're going to get NOE build-up, NOE distance measurements out of it, but the quality of that data may not be quite as good. Not that much worse, but a little bit worse. So if you can make the solvent low viscosity, that's going to help. We don't degas the sample. We do not remove oxygen from our samples, and the reason for this becomes obvious as we go through. But essentially, we want our NOE pairs, our nuclear spins, to all have homogeneous relaxation. We want them all to relax at the same rate. Of course, they don't, but the presence of oxygen helps them to relax homogeneously. So this is a good key. If you degas the sample, you are going to make this worse. How much worse? I'm not entirely sure. We've currently got a student literally this morning working in the lab to study what happens when you add oxygen to these samples and when you remove oxygen from these samples and trying to quantify some of this. So I'll get back to you in the near future. In terms of acquiring the data, we just use standard NOE experiments straight out of the box. We use 1D double pulse field gradient spin echo NOESYs or simple 2D transient NOESYs. We use mixing times around about, and this is all ballpark figures, 300 to 800 milliseconds. If you worry about these things, and I'll show you why you don't really need to in a moment, but if you do, you can measure a build-up curve, such as shown in the bottom left of the screen there, and then the mixing time that you want to use should be somewhere around about 50% of the mixing time where the peaks hit their maximum. So in this case, we're seeing NOE build-ups where they max out at about 1,000 milliseconds, so we would use a mixing time of about 500 milliseconds. If you use a more viscous solvent, DMSO, something like that, this whole build-up curve will collapse towards the left. The maximum would come out at about 500 milliseconds, so you'd use something around about 250, 300 milliseconds for analyzing something like a small molecule in DMSO. But as you're going to see, we're actually going to fix it so that we don't have too much curvature in our NOE build-up curves. And finally, one of the big keys here is relaxation delay. You've got to have reasonably homogeneous relaxation. You want all of your nuclei to have relaxed roughly similar amounts. And with a 1D nosy, the good news is you get this for free because your acquisition time is usually relatively long, about 4 seconds. You throw on a 1 second relaxation delay, you've got a total recycle time of 5 seconds, and that seems to be pretty good. We published the practicalities of this back in OBC in 2011 and essentially showed that if you're using a 2D nosy, you need the same 5 seconds of relaxation, of course, but because of the short acquisition time, that means you need to add a large relaxation delay, or you can acquire your data for much longer if you like to fill your computer disks. Entirely up to you. So when we're measuring these NOEs, the thing that we're fighting against and the thing that we want to be measuring is the NOE intensity versus this mixing time period. And what we can't have is this curve in the NOE buildup, because that curve comes about from external relaxation. Essentially, while we're waiting for our NOE to build up during the mixing period, all of the spins are also relaxing under the normal processes. And so that causes this curvature here. And some of our NOEs, and you can see it in the green here, relax a little bit faster than others, such as the blue one here, which is a bit of a flatter curve. And that causes us problems because we're going to compare their NOE intensities in order to extract distances from it. And if external relaxation differs between those two, then that's going to give us a difference in the NOE intensities, which is nothing to do with distance. And what we want is the NOE intensities to encode our distances with no other perturbing factors. So I'll show you how we get around that in a second. So a little bit of theory. I don't like equations a very great deal, but you have to throw them in here to at least understand what's going on. So throughout this webinar, I'm going to rely on a really simple assumption, and that simple assumption, I'm going to call it a fact here, but really it's an assumption. The NOE intensity between two nuclei, two spins, I and S, is proportional to the distance between those spins to the power of -6. Okay? We can go through the maths as to how you might come to this conclusion or not, but I'm going to make the assumption that this is true. In reality, the NOE intensity is proportional to the cross-relaxation rate, which is then proportional to R to the -6. So what are these terms? Well, the cross-relaxation rate is essentially the double quantum transition, alpha alpha to beta beta, minus the zero quantum transition, alpha beta to beta alpha. So it's the transitions where both spins flip. And the NOE intensity is proportional to that term, W2 minus W0, they oppose each other, but divided by a sum of W0 and W2 plus twice the single quantum transition. And the problem with this, with the assumption with my equation at the top there, is it ignores W1, which is external relaxation effectively. That is the normal old nuclear relaxation that we expect to see during an NMR experiment. The nice thing about cross-relaxation rates is that W2, the double quantum transition, dominates for small molecules. So for what we're going to be talking about today, pretty much we can ignore W0. It's not entirely true, but you can get away with it, hopefully, as you'll see. And that for large, slow-tumbling molecules, proteins and whatever, it's W0 that dominates and W2 has very little to do with anything. If you want to know the details of this, you can go and look in Neuhaus and Williamson's fantastic book on NOE structure and conformation analysis. It'll go through the equations to the joy of all. So how do we get to the simplification that I'm going to make? Well, depending on which equation and what regime you go into, you get a different equation. But here's a description of the cross-relaxation rate for a given NOE for molecules, for small molecules in the fast-tumbling regime. And you can see that that cross-relaxation rate is proportional to R to the -6, but with this large, rather cumbersome-looking term in orange here. But if we look at this, pretty much everything in here is a constant. Permittivity, pi, Planck's constant, gyromagnetic ratio of the nuclei, well that's a constant for any given set of NOEs. The frequency of those NOEs when you're working at 500 megahertz, all at 500 megahertz, so that's a fairly simple number, plus or minus a very small amount. And tau c, where tau c is the correlation time. Now tau c and correlation time cause me a great deal of pain when I try to worry about the accuracy of our NOE distance measurements. But specifically, tau c in this term is the correlation time for the pair of spins I and S. And that is how long it takes I and S to rotate around each other 1 radian in any given direction. That is the definition of tau c for one particular NOE. For the purposes of the talk today, I'm going to show you how and why it works in a minute. We're going to assume that the tau c values for all of the NOE pairs between proton 1 and proton 2 and proton 6 and proton 7 are all identical to each other, so that tau c is the same no matter what NOEs we're looking at. If we assume they're identical, then we're in the position where that entire term in orange collapses to something as nice and simple as this. Now this is the kind of equation I do like in my life. Sigma is equals some constant k times the distance to the power of minus 6. And the key here is that the kind of analysis that we're going to use to extract our distances is going to rely on the ratio of two NOE distances. So if I measure two NOEs, I'm going to call one of them IS and one of them reference, then those two NOE intensities, or the ratio of those NOE intensities, equals the ratio of their cross-relaxation rates. That's pretty simple, which equals the ratio of Ks times the ratio of the distances to the power of minus 6. And of course, if tau c is the same for every pair of NOEs that we measure in our experiment, then the two Ks cancel out, they are the same number, and we're left with a very simple expression where NOE IS over NOE ref equals the distance IS over the distance ref to the power of minus 6. So let's see this in a chemical context at least. Here's strychnine, our favourite rigid molecule. You measure an NOE for this proton. You can see NOE1 between the methylene groups and NOE2 between the vicinal protons. And we know the distance between the methylene protons is around about 1.8 angstroms. Out here, 1.75 or 1.85, it's about 1.8. That'll do for now. We measure the NOE spectrum and we see we irradiate one peak. We measure a nice strong NOE1 for that close contact, and we measure a second NOE for that second contact. And that means we've now measured the top line of our equation, the bottom line of our equation on the left-hand side, and we know R1, bottom of the right-hand side of the equation. Therefore, we can very easily calculate the unknown distance corresponding to NOE2. So if everything I've said is true, then we should be able to calculate that second distance quite easily. The really nice bit is we can also measure these two other NOEs in the spectrum, and then further NOEs for the rest of the molecule in order to extract all the distances we might be interested in. So the proof is always in the pudding in these things, but this really does rely, what's happened there? There we go. This really does rely on the fact that we can ignore external relaxation, that W1 term, and we can by using a trick. This is the panic correction. I'll explain this in a second. Now this has been was originally reported by Makora and co. Back in the late 80s, early 90s, but nicely demonstrated in 1D NOEs by Hu and Krishnamurthy in 2006. And panic is essentially what they call peak amplitude normalization for improved cross-relaxation. If it isn't NMR, you can't have a good acronym for it, vice versa. And what this panic correction does is accounts for the fact that when I measure two different NOE spectra, so here's two NOE spectra, one for proton A, one for proton B, we can see that the one at the top, the absolute intensity of the irradiated peak is different to the absolute intensity of the irradiated peak in the second spectrum. Roughly speaking, the top spectrum is half the intensity of the bottom spectrum. And that means that the bottom spectrum has undergone less relaxation, external relaxation, than the top spectrum. So we cannot compare the NOE intensities directly between these two spectra. However, panic is the very, well, I guess it's a complex acronym to explain a very simple process, whereby we simply take the irradiated peak, or in the case of a 2D NOESY, we would take the intensity of the diagonal peak from the slice of the 2D spectrum is how we normally do it. We can do it by cross-peak integration if you'd like to. And we set that to a value of 1. We know it's 1 proton, so we set it to a relative value of 1. Now in my group we set it to 1,000 because that gives us nice convenient numbers for our NOE intensities. And in the second spectrum we also set the irradiated peak in that second spectrum, which we also knew was 1 proton, to the same intensity. We've now corrected for that external relaxation, or that we've at least grossly corrected for it. And you can go and look at Hu and Krishnamurthy's paper to see all the maths behind it, but that's the net effect. And in practice, we take our curved NOE build-up curve that I showed you earlier, we apply panic, and we get very linear NOE build-up curves when we have a panic intensity on our left-hand, on our vertical scale. And you can see that we have much more linear build-up here. There's a bit of loss of intensity at the right-hand end, so it's not a perfect linearization of the NOE build-up curves, but certainly down below half the maximum intensity area, so 500 milliseconds in this case, we're very much in the linear build-up regime. So we should get very good correlations between the NOE intensities and the distances that they encode, and we can essentially ignore the effect of external relaxation. So let's just demonstrate this, again with strychnine here. I lied to you earlier actually, this is not the NOE spectrum for the protons on the outside here, it's actually H15A. So we radiate H15A, we see a large NOE for H15B, and then smaller NOEs for H13, H14 and H16. We can talk about those really tiny ones in the baseline later on if you're interested in the minutiae. The key here is the first step, is we set that NOE intensity for H15A to 1,000, and then we measure the NOE intensity for H15B. I just noticed we've got a mistake in the slide. I obviously reintegrated this between preparing this image here, but it's 175.7. Who cares about the fourth decimal place? 175 is the NOE intensity, or the panic NOE intensity, once we've corrected this to 1,000. The distance that it corresponds to in the molecule is 1.76 angstroms, and that's just measured off a molecular model or off a crystal structure, whatever you like. It's always 1.8 angstroms for a methylene group. You never get a 3 angstrom methylene distance. And so we're going to set that as our reference distance at 1.76. And then we measure the NOE intensity for H13 over here. That comes in at 44.21. We throw that into our equations, so NOE over NOE equals R over R to the power of minus 6. 44 over 175 equals R over 1.76 to the power of minus 6. You can believe my maths, I hope. That comes out with a distance of 2.22 angstroms. Plonk that into our table, and then when we measure H15A to H13 off our molecular model, we find that the distance should have been 2.26 angstroms. That's a pretty good deal. I'm going to be pretty happy with that, I've got to say. Then we do the same thing for H14 and for H16, and we find 19.43 and 23.8. We convert those into distances. We're expecting to see 2.56 and 2.48, and well, I wouldn't be showing this on a webinar if it didn't work. 2.54 and 2.48, and you can see here that we're off by about 1 or 2%. Now we're in the second decimal place in our errors in the distances here. So at this point, we've got to, we began to believe that this technique really is robust. And in fact, I'm going to make a point here. You can see that all of these distances are estimated by NOE to be slightly shorter than they are by the calculation. And one of the reasons for this could well be, and we'll see that it is, that actually our reference distance here of 1.76, we've assumed that's perfect. And it isn't. There's no reason at all why this estimated distance of 1.76 should be the right distance. It's allowed to have an error too, just like all these other ones. So actually, if we just nudge this distance up to 1.78 angstroms and redo the calculations, we find that all the others move up slightly. Of course, they all scale by the same amount. You move it up by 1%, and all the other distances move by 1%. And now we have an even better fit to the data here. Now, is that really something we should be doing? You'll see on the next slide that there's nothing wrong with it at all. So if we measure all of the distances for strychnine, all of the NOEs, then what we get, if we just start with a 1.76 angstrom distance for H15A to H15B, we get a curve where we can see a really good fit between the calculated distance, that's from the calculations, density functional theory or molecular mechanics, whatever you like, or from the crystal structure, which gives basically the same answer, compared to the NOE derived distances, and we get a very nice correlation, the y equals x line shown there in black. But you can see that most of the data is slightly to the left of the y equals x line. And that's simply because our H15AB distance, which is down here, has been slightly underestimated. If we decided that instead of 1.76 angstroms, it's 1.81 angstroms, then actually that shifts all of the data slightly to the right, and we get a much better fit to the data. We improve the average deviation from 3% down to 2.4%. The standard deviation stays about the same because the spread of the data hasn't changed, it's just the data's been slightly scaled. And that means that we've allowed 15A, 15B to have a small error in order to, and the consequence of that really is that we improve the quality of the error so that we get a best possible fit here to our expected data. So just to reiterate how we go through that, we essentially take a 1D nosy spectrum or a 1D slice from a 2D. We use panic in order to get all of the NOE intensities for all of our NOE spectra to be relative to each other. We use the -1/6 scaling, or the power of -6 scaling if you like, to calculate relative distances and then use one reference distance, typically a CH2, but it absolutely doesn't have to be. It can even be a flexible distance if you want it to be. The distance you use to reference this is purely to get everything, roughly speaking, onto the right scale, and then we scale that against our model system to see how good a fit we can get. And when we get a good fit, after we've scaled the data by allowing that small deviation in our reference distance, then we look at the quality of that fit. If the average error is 10%, it's not a good fit. If the average error is 2 and 3%, then it's a good fit and means that model could be a reasonable description of the system that we're looking at. I left out a small minor point when I was showing you this data, and I kind of ignored this bit of an outlier sitting up in the top of our plot here. And because we're good thorough scientists, we ignored that, published an OBC, and then went away and looked at this data point in more detail. Originally, we just thought that it was a bit of a deviation. It's a very weak NOE. It corresponds to an internuclear distance between H23B and H11B over here, which is about 4 angstroms. So it's calculated to be 4.1 angstroms, but we measure it to be 3.6. To convert that into NOE intensity, we measure 3.4 as our NOE intensity, but a 4.1 angstrom distance for this molecule should have given us a value about 3 times, 2.5 times lower than that. So there's a real deviation here, and we just assumed it was because these numbers are very small and there's a bit of noise in the background, and off we went. Basically, we didn't trust our own data. But the alternative explanation for this is actually that we don't have a single conformer of strychnine, which is the perfect rigid molecule we always assume. In fact, there's a second conformer of strychnine, or there could be, which has a much shorter distance, and that shorter distance dominates our NOE. And sure enough, when we went away and did some conformational searching, molecular modeling on this, we found that calculations suggested a second conformer where the distance between these two protons is much smaller because of the flexibility, very small, but flexibility around the 7-membered ring. By halving the distance between the two protons, you increase the intensity of the NOE by about 60-fold. So all it requires is a 3% or less population of this minor conformer in order to bring that data point down onto the line. And sure enough, when we estimated the population at around about, I think we said 2.7%, we then spent a lot of time doing some very high-level calculation to calculate the relative energy of these two conformers, and as you went to higher and higher level calculation, essentially the data converged on this minor conformer being somewhere between 1.5% and 3% of this system. So that kind of convinced us that actually this isn't an outlier, it's a real data point, and it's being generated by this conformational flexibility. And actually none of the other distances in strychnine are sensitive to this conformational flexibility, so it all ties up in that sense. Just to prove that we really weren't talking rubbish, it took us a wee while to get through this, but if we have this minor conformer here at room temperature, then as we heat up the sample, we should get more of it. As we cool it down, we should get less of it. And sure enough, when we do this, when we change the temperature of our NOE measurements, we can watch the apparent distance between these two protons get longer at low temperature as the major conformer dominates, and get shorter as the minor conformer comes up to about 3.5%, up at about 60 odd degrees. I'll point out that actually the error bars on this measurement are are slightly misleading. They actually represent the plus or minus 4% average error we get over all distances. The reproducibility of each of these data points is about plus or minus 1%. So this is a real trend here. And the black line actually is not the fit through the data, it's actually the expected behavior if we just throw the relative energies of these two conformers into the Boltzmann equation. And so we published that earlier this year actually in ChemCom. Welcome to go and have a look. So in terms of applying these to real systems, let's look at a couple of case studies very quickly. So going back to our conocosterol F, you'll remember that there were two possible diastereomers with two sets of internuclear distances, and when we applied our qNOE distance analysis, these are the values we found. H7 to H15, that's across the two rings there, is 2.73 angstrom, that ties up quite nicely, and sure enough, so do the other two distances at 3.4 versus 3.2 angstroms, 3.3 versus 3.3 angstroms, so actually there's a really nice fit to the data here. But of course we want to measure all of the data, and we did this comparing all of the qNOE distances that we could measure for conocosterol F excuse me, to what they were calculated to be for each of those two diastereomers. You can see a really nice fit for the, well, hopefully for the correct diastereomer, and a much less good fit for the other diastereomer. And this was a fairly convincing way for us to show the structure of the of conocosterol F. We also have chemical shift calculations and some other stuff in there as well, and that was published back in 2012. But of course that's a nice rigid molecule, so what happens when you get all flexible on it? Well, if you want to go to the other extreme, we were looking at some molecules with a collaborator of ours based on some work from Raoul Hoffman back in the 90s and around the turn of the century, where he proposed that the more methyl groups you can stick onto an alkyl chain, the more conformational control you can impart onto that chain, essentially saying that if you put a methyl onto each carbon of a chain like this, then you will force the molecule to take on a conformation where it avoids syn-pentane interactions, these methyl-methyl interactions like this. And so if you have the syn, anti, syn, anti, syn, anti, etc., homologated alkane as shown on the left there, that will take up a linear conformation of the backbone in order that the methyl group is always syn-pentane to a proton. Sorry, not syn-pentane, but syn to a proton, 2 carbons away. On the other hand, if you take the all-syn variant of that alkane, then in order to avoid these syn-pentane interactions, the backbone has to take on what is essentially every second bond taking on a gauche twist, and that will cause the molecule to form a helix. So the calculated structures are shown here on the right-hand side for these molecules. If we do a complete conformational search on what we think is going to be a linear molecule and what we think is going to be a helical molecule, we find that there are a lot of conformers. We're talking about 4,000 for the linear diastereomer, 10,000 for the helical diastereomer. That's conformers which are energetically accessible, of which about 20 of them would have calculated populations above 1%. And so what we did was to prepare these molecules, measure the NMR, compare it to these computed models, and see if it fitted. So the synthesis of this was enabled by some fantastic collaborators of ours. I'm not going to belabor this too much, there's one animation, but essentially they could add 1 carbon at a time to this carbon chain in order to homologate it in 9 steps and about a 46% yield. They could do all of this in 1 pot if they tried hard, but they tended to do it in 3 pots. It's absolutely beautiful chemistry, which is probably why we managed to get all of this into nature when we finally got there. When they made this, they found that the all-syn molecule in the solid state did indeed form a helix, but a much tighter helix. It's a 6-turn rather than a 7-turn than was calculated, but it certainly did all the right things. But really the proof for us is what happens when you put this into solution. And what happens when we measured the qNOE distances for this, we got exactly as we would hope, a very good fit between the experimental data and the calculated data. Now I'm more than willing to accept that there's a couple of outliers here. The blue fuzz there represents 1 standard deviation, I think, or might be 2 standard deviation for this molecule. So these are just on the limits of being outliers, but they're still within qNOE, and when I'm dealing with 18 conformers above 1% and 4,000 conformers overall, I'm not going to get too upset by standard deviation here or there. But there's a pretty good fit there for the qNOEs and a very good fit for the proton-proton and proton-carbon couplings, a story that I haven't really told you about today, or haven't told you at all. And when you combine those on one plot, you get a much better feel for the fact that the data really does fit with what's expected. That's for the helical diastereomer. When we move over to the linear diastereomer, we get an even better story to tell, fortunately. Very good fit of the qNOE distance analysis and the coupling constants as well, where actually we have much less data to go on, so we really relied on the qNOE distances in this case. And just to show you, I've showed you data that always fits, I haven't showed you data that doesn't. If you try to fit the linear experimental data to a helical model, you get a square, basically. The data just all falls off the plot. And we really go away from where we expect to be, particularly with the quantitative qNOE analysis. The average errors here are getting up around 10%, miles away from where they should be. So the final outcome, despite the fact that there is molecular flexibility in these systems and many thousands of conformers and a couple of dozen conformers which are significantly contributing to the quantitative qNOE analysis, we can still model these very accurately with what is, to be blunt, a pretty simple qNOE approximation, R⁻⁶, and it works with these molecules that are even relatively long, tumbling anisotropically, and relatively flexible. So it only remains for me to thank the people who did all the work, because I can't say that I sat down in front of too many spectrometers to do this. Catherine in the top left-hand corner there did all of the initial distance work. She really made this project start and made it fly. Maria Giovannacini was a visitor from our Italian collaborators on the conocosterol F project, and she did all the experimental analysis work on that. Matt Burns is the synthetic genius who managed to make all this homologation chemistry work. There was an enormous amount of work went into that one animation, about 4 years at PhD. And then the plots that came out of that, the NMR analysis of those homologated alkanes and the comparison to 10,000 odd conformers was done by Jess Baum and Stephanie Bull in our group, and the actual computational side and certainly the high-level calculations that we needed in order to really show that we were doing the right things came from Stephanie Asafi with our computational collaborators in chemistry in Bristol. So that's all that I had to say today. I hope you've found that helpful, and I'll be more than happy to take questions at this stage.